All right, lesson 35. I'm going to talk, whoa, oh, hold on. I forgot I had there we go. Let's not draw with my finger too much. We're going to talk about nuclear energy. Okay, so please pay attention to this particular notes because I'm going to talk about things we don't need to worry about and things that I want you to make sure that you do know for your final. Okay, so the first thing we're going to talk about is the decay series. So in a few lessons back, maybe two, I may have mentioned something about the stability of lead. And so in order to achieve a stable nucleus, many radioactive isotopes, so remember these are ones that are greater than 83, will undergo a series of nuclear equations. This series, this series, is known as a decay series, and it ends when a stable isotope is formed. And that stable isotope is usually lead. Okay? So this is an example of, Ceres thought I was talking to her because I kept saying Ceres, not you. This is the uranium decay series. Okay, so it starts off with uranium-238, goes through alpha, beta, beta, alpha, 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 and then once it gets to polonium, it can go a variety of different ways, but inevitably it's going to end up at lead, which is element number 282, element number 82. Okay, you do not need to memorize the decay series. What you do need to know is what a decay series is and what it usually leads to. All right, so kinetics. All radioactive decay series follow a first order kinetics, which we talked about back in chapter 12. And this means we can use those same reactions we've already used in this section, and we're going to substitute K for lambda instead of K. And so what that ends up looking like, our two equations we had were K, which is now going to be what used to be the rate constant is now going to be the wavelength, the lambda. And if we solve for the natural log of 2, that becomes 0.693. So that's a constant. So this can be used to calculate the half-life. Okay? If we know the rate of decay. The second is one of our integrated rate laws, which is if we know a certain amount, if we start with a certain amount and we know how much we have, or we want to know how much we have after a certain amount of time has passed at a certain decay rate. This also is going to translate into the following. I want to make sure I don't make any mistakes on writing this down. Okay, so this could be used to calculate how much is left or how much time has passed. Okay, so these are old news. Okay, the only thing we're taking is we're not going to use K, which is the rate constant. We're going to use this lambda, which is going to be the nuclear decay constant. All right, so there are a few differences between the rate constants we talked about for normal equations and the ones for nuclear equations. The rate constants for nuclear reactions can vary greatly, meaning they can decay, the half-life may be a couple of seconds or it can be millions of years. So one of the examples of this is carbon-13 has a very long half-life. I think it's 5,000. I get it mixed up with how many feet are in a mile, but it's roughly 5,300, I think, years. And so it lasts a long time, which makes it a really great radiometric dating tool, but it wouldn't be useful in imaging. So in imaging, you want it to last at least, a couple of minutes, hours, so that you can take the image, but you don't want it to stay radioactive in someone's body for much longer than that. Now, rate constants for nuclear reactions are also unaffected by temperature and pressure, which also makes them really great for imaging and for like radiometric dating and things like that, is because we do know or we know that they're not going to be affected by time and pressure, which those are both going to be factors with things that are buried under the ground for a long period of time under a lot of pressure, or maybe at a high temperature. Okay, so what are some other ways that scientists use nuclear kinetics? Well, you've probably have already picked up on this now. The radiometric dating, which there's different kinds, and then the medical imaging. And there's also different radioactive isotopes that you use based on what type of imaging you're doing. Okay. So one main use is radioactive dating. The most common isotopes used are carbon 14, uranium 238, and potassium 40. So most of the time, carbon 14 is going to be used in living organisms that are, well, once living organisms, things that are now dead because they eat carbon. And this ratio is something that is constant. Upon death, you stop eating, and so the decay of the carbon is going to stop. So carbon 14, which is found in nature, is going to start decaying automatically to nitrogen 12 through emission of an electron. And what this means is that the ratio is going to change. So this is going to be depleted. And I was not all that close. I know I said carbon 13. It's carbon 14. I was thinking of NMR. Carbon 14 has a half-life of 5,730 years. So I was a little off. But I get that and the 5,280 feet in a mile mixed up. Okay. So mainly used in living organisms that once dead stop eating, and we can use this ratio between the disappearance of carbon 14 to determine how long that organism has been dead. Uranium 238, well, it's going to decay into lead, as we said before. This is really useful to date really older things. That did not make sense. That was really bad English. To date older things. The reason why is because its half-life is 4.5 billion years. So it takes 4.5, let's write this right. I am struggling to write today. I guess it's Monday. 4.5 billion years. So if we have 100% of uranium, it's going to take 4.5 billion years for it to decay to half. And the way that they monitor this is they're looking for, like if they're looking at a rock. These are not living things. But they're looking at rocks and they want to know how long it's been. Oops, why did I do that? They're going to look at the lead-uranium ratio, which is going to tell them, because everything starts off with uranium at 100% and decaying to lead, we can determine how long it's been. So this is kind of how they date older geologic features and things like that, because we're kind of saying, we're working backwards, more or less. We're using the ratio to then predict how much time has passed. So it's not a solid science, but it's a pretty strong use of isotopes to date things. Another one that's really useful for rocks, specifically volcanic rocks, is the potassium 40. And what they're looking at is potassium-argon ratio, because potassium 40 has a half-life of 1.2 billion years. So not as long as uranium, but pretty long, and you have a high level of these isotopes specifically in volcanic rocks due to a variety of other things that's without the scope of the course. And so these are just examples of different ways they can be used. Now, in medical imaging, your book is going to have a whole variety of things, and I recommend looking at those. So, for example, iodine is used for thyroid imaging. because we know that iodine gets taken up by your thyroid, and so they use a radioactive isotope of iodine, gets taken up in the thyroid, and then they are able to image it. But there are others. Okay, so make sure you look through the book. There's a table, a section. Just I would briefly go through those. At least be familiar. I know bismuth is one, gadolinium is one. My mind's kind of drawing a blank there, but it could show up on the ACS test. I do know that nuclear chemistry tends to be kind of a bigger topic on the ACS exam, and it's great because we just usually finish this topic right before you guys take it. All right, so we are not going to talk about transmutation. It doesn't show up so much in your book, not at a high enough level to worry about covering it at this point in the semester. I want to focus on things that are more likely to show up. Now, we're going to talk a little bit about transuranium elements. So, let me zoom out. Elements with numbers greater than 92, so uranium, do not exist naturally. So I hope you knew that before today. If not, now you know. So the reason why we have those elements are because we have created them, isolated them just long enough to identify and characterize them, and then they go away. So they're man-made, and the person who makes them usually gets the naming rights, and so that's why they have such weird names. They used to be named after countries, or kind of like with nods to certain countries, but now the naming is just crazy. And so the way that they make them is by using a particle accelerator, and elements up through atomic number 118 have been synthesized, and all of which of them are radioactive because they're not naturally occurring. Their energy is having to go into forming them, therefore they're not going to stay together very long. And the bigger and the heavier that they are, the harder they are to isolate and characterize before they then disappear. So making an element is a really big deal because it's very difficult to do. The elements created so far are known as super heavy elements and have half-lives of fractions of a second. So they're not very useful. They don't live very long. And it's thought that there might be what's called an island of stability at higher numbers of neutrons and protons. And so we see this up here. Okay, this is our band of stability and the sea of instability, which is just a strange thing. And that there might be this island up here. If we can get there, we might see that they are super stable and they don't undergo spontaneous fission or anything like that. Now, we are not going to worry about why this would cause an island of stability. In fact, very few books even talk about this. But what is important is that you do understand that things greater than element number 92 are man-made, they are not naturally occurring, and they don't stick around for a long time. So they're not very useful really in anything that I can think of. The main thing is creating them is kind of just a very impressive thing to be able to do. All right, so everything we've talked about up until this point, believe it or not, was nuclear fusion. Small things, fusion. Things, I'm sorry, we have not talked about that yet. I got this mixed up with my other class. Now we're going to talk about nuclear fission, which fission is the process in which heavy nuclei, mass number greater than 200, divide to form something smaller of an intermediate mass and one or more neutrons. Okay, so something heavy breaking apart into something smaller. So that's an important definition. Okay, nuclear fission. Okay, breaking apart. And so using the table, it says to explain, given the nuclear binding energies in the table below, that the fission of 235 is of use. And so if we look at the nuclear binding energy compared to strontium and xenon, we can see that it's going to have more energy comparatively. Okay, and so the reason more energy than these, right? Because remember, if it takes that much energy to bind, it's going to release that much energy when you break it. So uranium is capable of releasing a large amount of energy. during nuclear fission. Okay, this is what makes it such a good source of nuclear energy. It lasts a long time, and then as it does decay, it releases a large amount of energy. So after it goes bombardment, so this is a little particle that's going to bombard the uranium. The uranium is going to start to divide into smaller things. And then once we see the strontium is going, and xenon are the next, the products, the intermediate products, which also release a lot of energy. Okay, so one uranium can go on to create a lot of energy. So then this says, what would you expect the next step in the reaction to be? Well, the two particles, the strontium, are going to become 4. So strontium is going to break into 2, xenon is going to break into 2, okay? And then so on and so forth. Excuse me. I hope y'all didn't just hear me burp. That's embarrassing. Why doesn't all uranium undergo an endless chain reaction? We're not going to worry about that. It's not going to show up on your ACS exam. We're also not going to worry about the design of an atomic bomb. Okay, so omit those 2 questions. We're not going to talk about bombs. So energy production. So I said a minute ago that uranium was useful for nuclear energy. There are not a lot of nuclear plants in the world. There are probably more than what we would like to think of. They are particularly great at harnessing energy, but very dangerous. So in 2011, in Japan, Fukushima plant underwent a nuclear meltdown. So one of the reasons why they're not great, due to a tsunami, which happened because of an earthquake somewhere else in the world. And then Chernobyl is a great example. I think that was like in the 80s or 70s or 60s. I can't remember exactly. And then there was also the 3 Mile Island incident in outside of New York, where there was a meltdown as well. So the problem with the nuclear power plants is once they start melting down, it's very hard to control. In fact, you can't. And so it just releases a lot of energy, radioactive energy, which is just bad for everything around it, the plants, the animals, the people, the everything. So if you don't know anything about a nuclear meltdown, I would look at Chernobyl. It's probably the best example. It was 1986, so it was a year before I was born. And this happened over in the northern part of Ukraine. And you can see some pretty amazing YouTube videos. If you want to lose hours of your life to YouTube, go look up Chernobyl videos. From a biological aspect, it's really interesting because we see that life is starting to come back to Chernobyl, but it looks different than it did before. And but it's thriving life, which is interesting. So this is an image of a simplified model of a nuclear power plant. You have your uranium fuel rods, your control rods, which help to control the reaction. You have this shield, which the shield is going to be made out of lead, concrete, and it's going to be very thick. It's going to retain all of the radioactive energy coming out to protect all the people at the plant and protect the parts of the plant. You're going to have this heat over here. It's going to come through here, and it's going to heat this water. The water is going to generate to steam, and then usually there's some sort of fan, which that doesn't look like a fan. I don't think I can draw a fan. Oh, that's not too bad. A fan, where once the steam is generated, the fan is going to then circulate, and that's going to generate electricity. Okay, so that's kind of like the simplified model of a nuclear power plant. And this is called the light water reactor. So the purpose of the water becomes liquid to gas. That gas then turns the turbine around, and just like our turbines, the spinning turbine generates electricity. Okay, so a bit comfortable describing this. Your book has really great information, and this lecture should not be that long, so that you can hopefully go back and look at your book and make sure you can read about these nuclear reactors. Okay, We're not going to talk about enriched uranium. And because we didn't talk about the atomic bomb, we are not going to talk about the nuclear reactor. Now, the difference between the light water and the heavy water reactors is it says, what is heavy water? So heavy water is called D2O. It's just like water, H2O, except for this is called deuterium. And deuterium is one of the 3 isotopes of hydrogen. And deuterium has the isotopic formula of this. So it's hydrogen with 2 neutrons. Okay. A heavy water reactor does not need to use the enriched uranium because the heavy water absorbs neutrons less efficiently, so it's not stealing energy from the uranium. This allows more to react with a small amount of uranium present naturally, so it means less uranium, less danger. Canada is currently the only country using a heavy water reactor, and this is as of the print of the book, which has been a few years. This allows them to stay away from having to make enriched uranium associated with weapons technology. And the amount of hydroelectric power they have allows them to make heavy water relatively inexpensively. But the problem with heavy water is you can't, you can reuse the heavy water. However, it's now waste, and so you can't get rid of heavy water like you could regular water. So light water reactors take water that's present in everyday life and just run it through the plant. Heavy water cannot just be disposed of that way, and so because it can be reused, it kind of solves that problem. But if a nuclear power plant were to need to be shut down or to become malfunctioning, the heavy water leaking out into the water systems would be very dangerous because then you would have D2O mixed in with water. So it just poses another risk. And we're not going to talk about the breeder reactors. Okay? All right. So hazards with nuclear reactors as an energy source. Accidents are common, which is kind of sad. We have 3 that we know of in the last 100 years, because 3 Mile Island was in 1911 or 1913, sometime in there, around the Titanic area. The ideal locations for a power plant, I hope you're not saying your backyard, probably not, but the ideal locations are rural areas. They want them near cities where there's a large population, for the exact reason of Chernobyl, for the exact reason of 3 Mile Island, for the exact reason of Fukushima, that if you have a lot of people living near a nuclear reactor and you have a meltdown, a lot of people are very, very hurt because you can't get them out of the city fast enough. And so it's a hazard to the community. But finding a very rural area is hard because the rural areas that we have are in the desert. And one thing you don't have in the desert is water. One thing that nuclear power plants have to have, water. So when you put them near water, you're automatically putting them close to people most of the time because humans, we need water, and that means we have to live near water. Another concern, which I'm hoping someone in this classroom is going to quote-unquote grow up to solve this problem, is that radioactive waste is associated with plants. So one thing that's very interesting, at least as far as I've looked into it, is that Europe has apparently, I mean, they're saying this and we're trusting it, but they have a system set up to handle radioactive waste as they generate it. We in the United States do not, as far as I know, and most of our radioactive waste, whether it's through weaponry or something like that, most of it gets put in some mountains in Nevada, as far as I can tell, because again, no one's telling you exactly where it's going, but it is a concern that if we continue to rely more on nuclear energy in the future, that we just simply don't have the systems in place to handle that waste. And the second is that people, which this kind of comes with persons, please stop. He's firing a pop gun 3 inches from my ear, and I know y'all can hear that. Oh. Accidents are common, therefore people and nature, that shouldn't say damage, that should say are in danger. Okay, so I'm going to go ahead and give you a hint that this will be a short answer question on your test. I'm not going to write that out there because I hope you watched my video where I told you to stop muting me if you're muting me. If you've made it this far, you now know one of the short answer questions on your next test. In fact, Anderson, can you get me a highlighter? I'm going to highlight this question so I make sure to write it on there. I'm highlighting it right now, folks, so you know. Okay? All right, highlighting it in, what color are you getting me? He's getting me yellow, so I'm highlighting as a short answer for your test next Friday, May 1st. All right, see you for the next lesson.